Welcome back into the quantum realm. My name is Masha, and I'm thrilled to continue our journey into the captivating world of quantum physics. In our last episode, we explored the mind bending concepts of wave particle duality and the wave function. And today, we'll dive deeper into fundamental concepts that lay the groundwork for understanding this fascinating field. Bringing us to episode 2 of our journey. Who let the cat out of the box? So let's get right into it, shall we? To start off, I would love to talk about arguably the most important particle property in the quantum world, without which it would be impossible to understand anything else: superposition. So, we already touched on this subject in the previous episode. Subatomic particles cannot simply exist in one state at a time, as well as we can't simultaneously know their position and momentum, until measured, of course. And the same applies to their physical properties, like spin and polarization. This happens because subatomic particles exist in the state called superposition. Superposition occurs when two or more waves overlap in the same space at the same time, causing them to either form constructive or destructive interference. So, the black and white strips from the double slit experiment. In mathematical terms, remember how in wave function the particle's position of space is given by the x-axis, and the probability of finding these particles given by the y-axis. In superposition, it means that its wave function simply has two values in different places, creating an equal probability of finding the said particle at two different places. So there are two separate amplitudes that refer to the same particle. Good way of thinking about superposition through the real life analogies is through the thought experiment known as Schrodinger's cat. It was originally proposed in 1935 by physicist Erwin Schrödinger in order to illustrate the absurdity of quantum objects, then applied to macroscopic objects. Just a disclaimer, this is just a thought experiment, meaning that absolutely no cats were harmed. With that said, imagine a cat in a sealed box with a radioactive atom that has an exactly 50% chance of decaying. If it decays, the cat dies. If it doesn't, the cat lives. With the box sealed from the outside perspective, we have no idea if the cat is alive or dead. Not until we open the box and check on the cat's well being firsthand. But until then, the cat exists in the superposition of being alive and dead at the same time, which I know, it sounded just as dumb when it was first introduced, since it's impossible for cats to be both dead and alive. But now we know that large objects like cat actually lose their superposition not because it's not real, but because of decoherence. Decoherence occurs when quantum systems interact with its environment, causing it to lose its quantum properties. Decoherence is the reason why our world is so different from the uncertain and probabilistic environment in the quantum world. Our constant interactions with the surrounding objects break those delicate quantum states, and as a result, we are able to see the objects at one state at a time. Now, let's move on to our next exciting keystone of quantum physics: quantum entanglement. This is where two or more quantum particles become linked, or in other words, entangled, meaning the state of one particle instantly influences the state of the other upon measurement, regardless of the distance between them. Our famous physicist, Albert Einstein himself, called this phenomenon spooky action at a distance, since this phenomenon implies communication faster than the speed of light, which should be impossible considering Einstein's rule of relativity, which states that the laws of physics are the same for all non accelerating objects, and that the speed of light is a constant for everyone. A good analogy For a better understanding of this would be if you have two coins that are not entangled. Then you flip your coins, they might land heads or tails, independently of each other. So flipping one coin would not have any impact on the other, meaning that each one of them has an exactly 50-50 chance of either being heads or tails, no matter what. But if you could entangle those coins so that if one of them lands up heads, the other one would be tails, no matter how far apart they are. Let's imagine that we decided to take those entangled coins into space, far away from each other. So they're placed on two rocket ships, going in the opposite direction from one another. After they were traveling for 10 years, the crew from both ships are instructed to flip the coins and set the outcome to the other ship. But since those coins are entangled, the moment the first coin flip turns out to be heads, it's an instant guarantee that the second coin will land tails. And even though it would take literally years for the information from one ship to be passed to another due to the distance between them, the coins, they just do it instantly. So, does it mean that communication faster than the speed of light is possible? No, not really, since no new information is actually being passed this way. The particles were already lined to each other in their superpositions, and the act of measurement just fixed them in one state of their possibilities, meaning that the outcome of a set operation is completely random every time. And without any control of what exact information you are transferring, you cannot utilize it as a way for communication. It is similar when you find one of your gloves from the pair. You would immediately know the type, size, color, and other features from the other glove, no matter the distance between them. But no new information traveled from one glove to another, as it has always been that way. Moving on to our last phenomenon of the day, quantum tunneling. Quantum tunneling refers to a phenomenon where a particle is able to pass through a potential energy barrier, even if it lacks the energy to overcome it. For a better understanding, we can compare it to classical physics, where we can imagine a ball and a hill that it wants to overcome. But if the said ball doesn't receive enough of a push, it would never be able to cross this hill. In scientific terms, if an object like a ball lacks the energy required to surpass the potential energy barrier, in our case the hill, it would never be able to get to the other side. But as we learned from the previous phenomenon in quantum physics, nothing is that simple. So, if you would investigate an electron instead of the ball, and some kind of potential barrier instead of the hill, even if the electron does not possess enough potential energy to overcome the said barrier, there's still a 15 chance for it to end up on the other side of the obstacle. It is important to note that when I say the potential energy barrier, it doesn't directly mean a literal barrier, like a wall, but rather any form of energy that affects the electric field barrier behavior, not allowing the particle to surpass it. An example would be a positively charged alpha particle that is approaching the positively charged nucleus. And due to the Coulomb's law stating that opposite electric charges attract one another, thus comparable charges repel one another. And due to both of the nucleus and alpha particles being positively charged, as well as alpha particle clearly lacking the energy to overcome the power of the whole nucleus, making it a potential barrier. This phenomenon can again be explained by the wave property of the subatomic particles, as well as the Heisenberg's uncertainty principle, that states that we are unable to know the exact location and momentum of the particle, only the relative probabilities of where we are most likely to find it. So, similarly, in quantum tunneling, we have an extremely high probability of finding the particles on its original state of the barrier, but still a non-zero chance for it to be on the other side, which we already understood in episode 1, but now we're left with the question of how does this particle surpass the impossible barrier? The uncertainty principle doesn't really suggest that the particle teleports to the other side, does it? Not really. This phenomenon occurs due to the wave nature of a particle, since it doesn't occupy a single location in space, but instead spreads itself around and surrounding space as a probability distribution. In other words, it exists in the superposition. So, this probability distribution tells us that this particle can be everywhere in the surrounding area, including the other side of the barrier. As a result, once the measurement is made and the wave function collapses into a singular state, it might end up on the other side since, even though the chances are extremely low, they're still not zero, especially considering the unthinkable numbers of particles available on the subatomic level. Even the lowest of non zero probabilities are able to come true. I hope you've enjoyed our exploration of fundamental concepts in quantum physics, from superposition to quantum entanglement and to quantum tunneling. All these ideas lay the groundwork for understanding the complexities of the quantum realm and will provide a great assistance for the upcoming episodes, since only with the understanding of how the quantum world functions, we're able to actually dive into more fine aspects of what we get from its subatomic universe. So, if you're interested in learning even more about quantum physics, stay tuned to continue our journey right into the quantum realm.